You're tuned in to the Deep Dive. And today we're looking at something, well, really fundamental to pretty much all our electronics. It's the reliability of BGA solder joints, ball grid array.
Right, those little tiny connections holding the chips onto the boards.
Exactly. We're diving deep into how they stay strong, how to avoid cracking, and also those little bubbles inside, the voids.
Yeah, voids can be a real pain, and it all comes down, surprisingly often, to the design of the pads on the PCB, the printed circuit board.
Oh, okay.
Specifically, we're comparing SMD, that's solder mask defined, and NSMD, non-solder mask defined pads.
And we've got some great source material for this deep dive. There are articles and also a really interesting YouTube discussion from Sutu Working Bear over at Research MFG.
Yeah, they've really been looking into this hands-on, doing their own experiments and everything, tackling real-world problems.
So the big questions we're trying to answer for you today are, which pad design, SMD or NSMD, holds up better against cracking? When you drop your phone or something.
Right, the stress factor.
Yeah. And then which design might actually help reduce soldering defects, like those voids or bubbles we mentioned?
And it's important to say up front, there's no simple answer here. It's not like one is always better.
Ah, okay. So trade-offs involved.
Definitely. It's all about trade-offs. What works best really depends on the specific device, what it needs to do, what it needs to survive.
So our goal is really to equip you, the listener, with a better grasp of these choices and, what they mean.
Exactly. A deeper understanding of the design considerations.
All right, let's get into it then. SMD versus NSMD. What's the basic difference we're talking about here?
Okay, think about the solder mask. That's usually the green coating on the board, right? With SMD, solder mask defined, that green layer basically dictates the size of the copper pad that the solder ball connects to. It covers the copper right up to the edge of where the solder should go.
So the mask defines the spot. Got it. And NSMD?
NSMD is non-solder mask defined, sometimes called copper defined. It's the other way around. The copper pad itself is actually smaller than the opening in the green solder mask.
I see.
So when you solder, the solder flows onto the top of the copper and wets up the sides of the copper pad too, within that larger mask opening.
Okay, I think I can visualize that. One's defined by the green stuff, the other by the copper itself.
You got it.
Now, let's talk strength. Our gadgets are getting smaller, thinner, we carry them everywhere. Those BGA joints must be under a lot more stress these days.
Oh, absolutely. And Ahidi, Working Bear, they definitely encountered this. They were seeing BGA joints cracking.
Even with underfill, I thought that was supposed to prevent cracking.
Yeah, even with underfill, that extra epoxy support, that tells you the stresses were, well, pretty significant.
Wow. So what was the first suggestion they got to fix this?
Well, the PCB manufacturers they talked to initially suggested switching to an SMD design.
Why SMD?
The thinking was, sort of, that the solder mask overlapping the copper pad would anchor it more strongly to the board, to the FR4 material underneath, making it less likely for the whole pad to get ripped off when the BGA was stressed.
Did they test that idea? I think you mentioned some lab tests.
They did, yeah. They did some pull tests directly on the pads themselves. This was without any solder balls, mind you, just the pads.
Right, just the pad adhesion.
Exactly. In that specific test, the SMD pads did show higher pull strength, about 53% higher than NSMD, actually.
Whoa, that sounds like a lot.
It does. But remember, that's just the pad pull strength, not the whole solder joint with the ball. So, useful info, but not the full story.
Okay, good point. So SMD seemed stronger at the pad level in that test. But what about actually making the solder joint? What are the pros of NSMD there?
Right. For the soldering process itself, NSMD often has advantages because the solder can wet onto the sides of the copper pad, not just the top.
Like you said before.
Yeah, you generally get better solder wetting. The solder flows and bonds more easily. Plus, the position and size of the NSMD pad are defined by the copper etching process, which is usually more precise than placing the solder mask.
Okay, more precision.
And critically for designers, because the copper pad is smaller, it leaves more space between pads for routing those tiny electrical traces that connect everything up, especially important with fine-pitch BGAs.
Yeah, routing must be a nightmare sometimes. But what's the flip side for NSMD? What about its strength in the final product?
Well, the potential weakness is that smaller copper area. It has less surface bonded to the board material, so it could theoretically be easier to tear off under stress.
Makes sense. Less glue area, basically.
Kind of, yeah. And also, sometimes the exact shape of the NSMD pad can be a bit uneven if a trace has to run right into it. And very often, for products that need to pass drop tests, NSMD designs end up needing that underfill anyway for extra robustness.
Okay, so better solderability maybe, but might need that extra underfill help for toughness. Let's swing back to SMD then. What are its advantages for overall strength?
The big advantage for SMD strength is that solder mask overlapping the edges. It acts like a reinforcement, holding the pad down more securely.
Like a picture frame holding it.
Exactly. A good analogy. It improves the adhesion to the FR4, which generally helps it survive drops and tumbles better.
Okay, a stronger foundation. But there must be downsides to SMD too, right? Especially for soldering.
There can be. One issue is that the solder mask material can expand a bit when it gets hot during reflow soldering.
Ah.
And that expansion can slightly change the opening, maybe interfere with the solder paste making perfect contact. Also, aligning the solder mask layer isn't always quite as accurate as etching the copper layer.
So the pad position might not be quite as perfect?
Potentially, yeah.
Yeah.
And lastly, that larger copper area needed for the SMD overlap. Well, it makes routing those traces harder again. Less space between pads.
So it really is a balancing act. No wonder Pergolopoulos concluded there's no single best way.
Absolutely.
Right.
They stress that point. It completely depends on the product's specific needs, what kind of stress it will see, how dense the board is, cost factors, everything.
Right. So the theory and the pad-only tests are interesting, but what happened when they tested actual solder joints with the solder balls attached?
Okay, yeah, this is where their experiments got really practical. They did two main tests on actual soldered BGAs.
Yeah.
A shear test, which is pushing the ball sideways.
Like trying to slide it off.
Exactly. And a pull test, pulling the ball straight up, away from the board. And they did this for both SMD and NSMD pads.
What was the setup like for those tests?
Pretty thorough. They used 0.4 millimeter solder balls, which are quite common. The board was standard FR4 TG150 grade, 1.6 millimeters thick, with an E and IG surface finish. Electroless nickel immersion gold. It's a common plating for good solderability and shelf life.
Gotcha. And the solder?
SAC 305 alloy for both the balls and the paste. That's your standard tin, silver, copper, lead-free solder.
Okay. What about the test conditions, like speed?
Right. For the shear test, they pushed at 5,000 micrometers per second. The push tool was set at 10% of the ball's height. Now, they did point out that this shear speed was actually faster than the range specified in the standard test method, JGSD 22B117.
Okay, so maybe the numbers aren't directly comparable to tests done strictly by the book, but still useful for comparison between SMD and NSMD in their setup.
Exactly. Keep that context in mind.
So the results, what did they find? Pull test first.
Okay, pull test results. NSMD actually came out slightly ahead. Average pull force was 884.63 gram force.
NSMD.
SMD was 882.33 gram force. So very, very close.
Barely any difference, really.
Yeah, GG noted it wasn't a statistically significant difference. So maybe a tiny edge to NSMD in pull strengths, but basically a tie.
Okay. Well, what about the shear test, pushing sideways?
Ah, that's where things got more interesting. In shear, NSMD performed significantly better.
Really? How much better?
NSMD averaged 694.75 grams of force, while SMD only averaged 639.21 grams.
Okay, that's a more noticeable difference. So NSMD resisted that sideways push better.
Definitely.
Now, they also looked at vias, right? Those little filled holes in the pads via in pad.
Yes, they tested configurations with and without plugged vias under the pads.
And did that make a difference?
Generally, yes. Having plugged vias tended to improve both pull and shear strength for both SMD and NSMD pads.
So vias help overall.
It seems so, though PM mentioned the improvement wasn't maybe as huge as they expected. But here's a weird twist.
Uh-oh.
NSMD with plugged vias gave the best results in the shear test. But SMD with plugged vias actually gave the best results in the pull test.
Huh. That seems counterintuitive.
Yeah, they noted that specifically as something needing more investigation. Why SMD plus via was best in pull, but NSMD plus via was best in shear. It's complex.
Definitely. What about how things broke during the tests, the failure modes?
Very revealing. In the full test, standard NSMD pads often failed by the entire copper pad peeling off the board.
Ah, the weakness we talked about earlier.
Exactly. With NSMD plus vias, it was mixed, sometimes pad peel, sometimes the solder itself fractured.
Then SMD.
With SMD, both with and without vias, the failure was almost always a fracture within the solder joint itself.
Suggesting the pad-to-board bond was stronger with SMD?
That's the implication, yeah. The weak link shifted to the solder itself.
Okay. And for the shear tests, how did they fail there?
Similar pattern, mostly. NSMD without vias sometimes resulted in the pad being ripped off. SMD with or without vias usually resulted in the solder fracturing.
So putting all that experimental data together, what was Petrie's final take?
Their conclusion was, well, nuanced. They felt that NSMD with plugged vias did offer some improvement in pad bonding, especially resisting shear forces,
Okay.
but it wasn't like a magic bullet solving all strength problems. Despite the mixed results, they still kind of lean towards using NSMD with plug vias for BGA pads, especially maybe on the outer rows where the stress tends to be highest.
But with a big caveat, right?
A huge caveat. They really emphasize that the most effective way to prevent BGA cracking isn't just tweaking the pad design, it's tackling the root cause of the stress through good mechanical design of the whole product.
Right. Make the device itself less likely to bend or twist in the first place.
Precisely. The pad design helps, but it can't compensate for fundamentally high mechanical stress.
That's a super important takeaway. It's system-level thinking. Okay, let's switch gears now. Another big headache, voids. Those tiny bubbles inside the solder.
Ugh, voids, yeah.
Someone on the forum asked specifically, SMD or NSMD, which one is better for reducing those voids after soldering?
And this is another area where you find conflicting advice, which is interesting.
Oh.
Like what? Well, the sort of general wisdom you often find online is that NSMD is better.
Yeah.
The idea is that the exposed copper sides give gas more pathways to escape during reflow.
Okay, that seems logical. More escape routes.
But the forum user mentioned a book by an expert who apparently claims the opposite, that SMD is actually better for gas release, especially with lead-free solder.
Really? That's a direct contradiction. What did the person asking the question find in their own experience?
Their practical experience sided with the online consensus. They said they generally saw slightly fewer voids when they used NSMD, and they specifically had a big problem with a 0.4 millimeter pitch BGA using SMD pads. They were getting large voids, causing electrical shorts.
Ouch. Shorts are bad news. What did other people on the forum think?
Most people chimed in agreeing that NSMD usually meant fewer voids. There was also talk about how large copper planes or even silkscreen near fine-pitch BGAs could affect things like board flatness or solder paste printing, maybe making voids worse.
Okay.
The general feeling was, for really small pitch parts, NSMD is often preferred. Maybe even skip the silkscreen right nearby. For larger pitch BGAs, maybe SMD is okay, and you get the benefit of more consistent pad size and maybe better adhesion.
So practical experience seems to lean towards NSMD for fewer bubbles.
What was you?
They generally agreed with that observation. Fewer voids with NSMD.
And their reasoning, pretty much the same as the common wisdom. NSMD exposes those vertical copper sides. That means more area for the solder to wet, better solder flow, and critically, more ways for trapped gas to get out during reflow. They felt most research and experience points to NSMD for better joint quality and fewer voids, especially with BGAs.
Okay, but what about that specific case the user had? The 0.4 millimeter pitch BGA with SMD pads and shorts caused by large voids. Did Troy think switching to NSMD would fix that?
Not necessarily. For that specific severe problem, Troy suspected just changing the pad definition might not be enough.
What else could it be then?
They thought it was more likely related to the via in pad implementation, specifically how the via was filled. Maybe there was a dimple left in the fill, or maybe the resin used for filling was outgassing during reflow, creating those big voids.
Ah, so looking under the pad, not just at its edges.
Exactly, the details of the via filling process.
The user then provided a ton more detail, didn't they? X-rays, specs.
Oh yeah, they really laid it all out. X-rays showing the shorts, pictures of the bare board, the BGA specs was a 0.4 millimeter pitch WCSP, a wafer-level chip scale package with 0.28 millimeter balls, which were actually bigger than other balls on the same board.
Interesting. And the process details.
They used a very thin stencil, 0.08 millimeter, with tiny 0.21 millimeter square openings with rounded corners for the paste. The board was thin too, 0.7 millimeter, standard reflow profile, peak around 247 degrees C, about 60 seconds above liquidus. They said overall voiding was under 8%, which isn't terrible generally.
But they had those specific large ones causing shorts.
Right. And crucially, they mentioned they used to have a larger stencil opening, 0.25 millimeters, and got lots of shorts, so they downsized to 0.21 millimeter.
Okay, that's a lot of detail. What did Tree make of all that?
Well, they acknowledge that SMD pads can make piece printing trickier for fine pitch because the solder mask thickness creates a small gap, a standoff between the stencil and the board.
Affecting the paste deposit.
Potentially, yeah. But they also repeated that SMD pad size is usually more consistent than NSMD where traces enter, which can help when designing the stencil apertures. consistency versus potential standoff issues.
And the claim about SMD being better for gas escape?
DB remained pretty skeptical about that, saying it just doesn't align with most evidence.
Hmm.
For the void issue itself, they reiterated checking with the PCB fab about the via filling, probably copper plating for that pitch.
Okay. Anything else?
Yeah, they raised an interesting point about the reflow of an atmosphere. They wondered if using nitrogen N2 might counterintuitively be making things worse in some cases.
How could nitrogen make voids worse? I thought it was supposed to help soldering.
It usually does by preventing oxidation.
Right.
But the theory is it might also lower the solder's surface tension and increase the internal pressure within any forming voids, potentially making them larger or harder to collapse. It's not a definite thing, but something to consider.
Wow, okay. Another complex interaction. So what was the final advice for the user with the shorting problem?
The main suggestion was practical. Try experimentally reducing the solder paste volume even further. Maybe slightly smaller stencil apertures again.
Carefully, though.
Oh, absolutely. While carefully monitoring the joint quality, they strongly recommended using SPI solder paste inspection to actually measure the paste volume being deposited. You don't want to reduce it too much and end up with insufficient solder or weak joints.
So, careful, measured experimentation. Makes sense. That whole case study really shows how many little things can affect the outcome.
It really does. It's rarely just one single cause.
Well, this has been an incredibly thorough deep dive. It's crystal clear now for you listening that picking between SMD and NSMD pads for BGAs isn't straightforward at all.
Not at all. It's a real mix of factors, and like we said, no single best way for every single design.
So let's just quickly recap the main takeaways from all this.
Okay, so generally speaking, SMD pads tend to give you better physical adhesion to the board. They're often stronger against mechanical stress, like drops.
Right, the mask helps hold them down.
But NSMD pads usually offer better solderability. The solder wets more easily, and they potentially lead to fewer voids because gas can escape better.
Okay, strengths versus solderability voids, broadly speaking.
And the vias. Via in-pad, especially when filled properly, like with copper plating, seems to help both strength and electrical performance for either SMD or NSMD. It's generally a good thing if done right.
But focusing just on the pad isn't enough, is it?
Definitely not. For preventing cracking, the #1 thing is still good mechanical design of the whole device to minimize stress in the first place.
Yeah.
And for soldering defects, like those big voids causing shorts, you have to look beyond the pad type, via filling, solder paste volume, the reflow profile, even the oven atmosphere. They all play a part.
It really takes a holistic view of design and manufacturing.
That's the key. Understanding all these trade-offs helps you make much smarter decisions for your specific product and its reliability needs.
Absolutely. And to leave you with something to think about, as electronic devices face ever tougher reliability demands, think about handhelds, wearables, automotive, industrial environments, how might PCB and packaging technologies evolve in the future? How can we get past some of the inherent limits of today's BGA soldering and pad designs?
Yeah, how do we keep pushing that balance between mechanical toughness, electrical performance, and manufacturability? It's an ongoing challenge.
Definitely something to ponder. We really encourage you to check out the source materials if you want even more detail and think about how this applies to your own work or the devices you use.
Thanks for joining us for this deep dive.